Good morning, good afternoon, good evening, everybody. It's Wednesday, so it's EMinar day, and as people are rolling in, I'll do an introduction very quickly. Today we have a very apropos seminar from Bulent, and I'll discuss this in a bit more detail shortly. For those of you who are new here to this seminar series, you can go on this MTNet website, MTNet EMinars, and there you'll see a whole list of the EMinars that have occurred and that will occur, and you can get links and view the recordings and presentations of the EMinars that have happened, and you can register for upcoming EMinars. And in March, we have 3 EMinars scheduled. We have one coming, the one next week, Wednesday, is from Paula Ruff on technical insights into advanced numerical methods. The EMinar following, I think, is very exciting. I managed to get Paolo Del Aversana to agree to give us, he's been playing with a Chat GPT-3. So he's going to tell us about his very brand new experiences with that. And then the following week, we have Anna Platz on insights into different processing strategies using empty data from Western Bohemia. And then on the 4th Wednesday of March, we have a gap. So if anyone would like to present your work to the community, we welcome you to step forward. Today, though, it's my great pleasure to have Bulent talk to us on and give us the review paper that he presented in Turkey last September on electromagnetic studies in the Eastern Mediterranean region with special reference to major transform strike-slip faults. And I don't need to tell you how appropriate that we're hearing this today, given the very unfortunate humanitarian disaster that's occurring in Turkey and northern Syria right now. Very quickly, I won't read all these details. You saw them as you registered. But Bulent is at Kandili Observatory and the Earthquake Institute in Istanbul. He got his master's degree and then PhD from Tokyo. And then he was a MEX fellow. And his PhD thesis topic was on the western part of the North Anatolia fault zone, its seismogenic implications. So as you can see, Bulent's very, very familiar with these types of issues that we're facing today. During his postdoc research, he attended the Volcanic Fluid Research Center in Tokyo and as a Japan Society for Promotion of Science. And his current research interests are EM studies performed at active and passive faults. So at that point, Bulent, I'll stop sharing and invite you to share your presentation and give us your review.
Is that all right?
It's absolutely perfect.
Okay, thank you. Good afternoon, everyone. Thank you for giving me this opportunity. My name is Bulent and I'm joining this EMinar from Boğaziçi University in Istanbul. This presentation was originally designed and presented as a review talk at the 25th Electromagnetic Induction Workshop in Çeşme last year. So its target audience was EM researchers. But as you know, 2 devastating earthquakes took place 2 weeks ago, 2.5 weeks ago, at the junction point of East Anatolian Fault and the Dead Sea Transform Fault, which were the 2 of the faults I was referring in my review. Move it. Here is the outline. In the following 1 hour, I guess, I plan to present you a review on the relationships between the faults and their electrical structure. First, I will begin by describing the recent activity. So there will be a little bit of seismology. Next, I want to proceed with proceed by reminding you some basic concepts related to faults and earthquakes. After that, I want to focus some of the systematic EM studies performed on the three major strike slip faults located in the Eastern Mediterranean. In between, I will also like to give you a historical and global perspective to this topic. Almost 3 weeks ago, two catastrophic earthquakes took place, one after the other, near the transition zone between the East Anatolian Fault, it's somewhere around here, and the Dead Sea Transform Fault. The moment magnitudes of these earthquakes reached to 7.7 and 7.6 respectively. The first earthquake was expected, but whereas the second was quite a surprise to many people, including the authorities and seismologists. They were shallow earthquakes, that's why their devastation was huge. Around 10 prefectures with 10 million people were influenced by them. Unfortunately, we lost almost precious 40,000 lives, and there were more than 10,000 buildings collapsed. In my opinion, this is more than a disaster. And 2 days ago, another earthquake occurred somewhere around here with a magnitude 6.4. People are still discussing whether this is an aftershock or it's a separate event. Seismology is a very powerful branch of geophysics, and it can provide quite a lot of useful information. But other than that, the recent activity proved us several important facts. I borrowed these figures. These two figures are showing the clump stress change of the first event here and the second event over here. By the way, they are 9 hours apart. So if you check this earthquake, you will easily see that this area is loaded. 9 hours later, the second event occurred. So these recent activity proved us several important facts in my opinion. Firstly, it proved us that the stress transfer at the fault zones can be quite rapid. I don't know any other example in this region that two 7.5, above 7.5 earthquakes repeating each other with this much of speed. They also showed us that the large earthquakes may trigger another large earthquake. So these are separate fault lines. This one is occurring here, and the second one is occurring here. So this was quite unusual for many of us. And further, they showed us that we must be extremely careful when it comes to triple junctions. There are two triple junctions around here. This one is called Hatay triple junction somewhere here, and another one is here Maraş triple junction. So the earthquake took place between two triple junctions. This is also something unusual. The third triple junction is located somewhere around here. It's called Karlova triple junction. And as you can see, the load create a future event over it. So the idea is, how can other branches of science provide support to seismology? I think that's an important issue. Can we learn more about the faults and earthquakes by other methods? You might guess that I'm trying to bring the idea to EM, in particular magnetotellurics, so that we can get to know about the faults more. That's the basic idea behind this review, in fact. So let me start explaining my review and telling you my review. The designation of faults goes way back to the classical theory of Anderson in 1905. But it wasn't until 1965 the phrase transform faults was not included into the scientific nomenclature. In 1965, Wilson published this remarkable paper. Actually, he published 2 papers that year, but this one is quite remarkable in our because it's related to our topic. So he used the phrase transform faults, and then another thing he did is he defined the San Andreas fault, North Anatolian fault, and the Dead Sea transform fault as examples of transform fault. In the Middle East or Eastern Mediterranean, however, Sanket'in, a distinguished Turkish geologist, had already described North Anatolian Fault as a major strike-slip fault much earlier, in the mid-1950s. Recently, Schenger et al. Defined a transform fault as a transform fault is a strike-slip fault cutting the lithosphere and connecting two zones of divergent or convergent deformation, or even another transform. I guess Schenger et al. Was mentioning the recent activity in the latest part of this statement. So, for our purpose, understanding the fault zone architecture, especially at continental seismogenic zones, is indispensable. But as you can imagine, this is a very, very complicated topic. Let me open a parenthesis here. My generation of EM scientists were raised up by following a concept known as law of parsimony. Many of you may recall it as the Occam's razor, and thanks to Dr. Constable from Scripps, he successfully transferred the philosophical idea into geophysics. But the one I'm mentioning is related to the philosophy of. I often followed its rules to simplify or to better understand complicated phenomena such as faults and earthquakes. That's why I prepared this slide, and I gathered some information from hydrogeology, seismology, and EM model. At the beginning, they might seem quite complicated to you, but as a matter of fact, these figures were not plotted by me. They belong to prominent groups and established scientists. I just feed in more data into them. And my sole purpose of doing it was to have a concept model for a strike-slip fault system. Now, please allow me to use one of them. By the way, this one is showing the along the fault. This one is showing the across the fault. And this one is showing the map view. Allow me to use the across one to explain how the fault quakes, earthquake occurs, how the mechanism works. If we have a look at the fault zone, the fault zones are made up of three distinct zones. One of them is the core of the fault, which is not easily be seen at this scale. But then we have the damage zone, and we will have a protolith or country rock on two sides. We focus on the shallow area. There is a highly permeable zone that we call fault zone conductor if we are dealing with EM faults. If we are familiar with this phrase. I think this phrase is the origins depend on the Martin Answorth's models. So anybody who's studying EM and using fault zone conductors. So this highly permeable zone, as you go deeper, narrows down, and reaching to the base of the brittle ductile transition, it widens up. Or we can also say at the base of the seismogenic zone, it widens up. It can be considered as a zone of enhanced deformation, probably free. So at this point, let's assume for a while that in the upper mantle depths or lower crustal depths, partial melting is taking place. When partial melting occurs, it's also known that a kind of metamorphism that we call as prograde metamorphism takes place. Prograde metamorphism is well known with its fluid extraction. So it means that the materials, the rocks or minerals there, are giving out fluid. So I'm trying to tell you is that at these depths we may have some free fluids. These free fluids, when they ascend to a certain depth, let's say they reach to the base of the brittle ductile transition or the base of the seismogenic zone, they make use of a model that is called the fault wall model. Another name for it is seismic pumping, to infiltrate into the shallower levels of the fault zone. by using a highly fractured network. So once the fluids are inside the seismogenic zone, or inside the fault zone, they cause hydrofracturing, or they cause chemical dissolution. They cause many other processes that I cannot count here. Such a complicated. The metamorphism type changes here. It becomes retrograde metamorphism. Retrograde metamorphism is well known for sucking the fluids this time. So hydrated minerals are found at these depths. Talking about mid-crustal depths now. And these fluids are also responsible for, these migrating fluids are also responsible for lubrication promoting agents. I mean, transfer of lubrication promoting agents, such as pulp or clay. Once these fluids and hydrated minerals are under great pressure, once they are overpressurized, they tend to reduce the effective normal stress. They tend to reduce the shear stress eventually. And all of these processes eventually end up in the mechanical weakening of the fault zone. The asperities are no longer holding each other because they are somehow somewhat apart from each other. And this allows the earthquake to occur. As I said, this is a very, very complex process, but I tried to simplify it and make up a story. You might ask why I'm explaining this to you, because in a moment I will be showing some color models of EM. And I would like you to read those color models considering these information. You might need to keep this information at the back of your minds when you are looking at those blue and red models. They are not just showing us the conductivity. There are a lot of processes. So I tend to see this process like completing a puzzle. So if we have a concept model of a strike-slip fault system, this position, we might fill in the gaps. We can find similarities and discrepancies with our EM models, and we can complete the picture. That's the idea. That's why I want to have a simple story out for an earthquake. Okay. So far, I presented you the general properties of strike-slip faults and the fluid's role in the earthquake generation process. Now, let's approach to the problem from the EM point of view. I think it will not be so wrong to claim that the telluric occurrence method was the origins of EM studies, and it may go back to late 20s or early 30s, and experiments performed by Schlumberger brothers. A familiar name here is Shalkunov, who is the person who first defined the electromagnetic impedance. And about 10 years later, the pioneering works by Vikitake and Kano and Cagniart appeared. They set up the fundamentals of the MT that we use today. 1 year after Cagniart's study, an opposition came from James Waite based on the boundary condition. It became a debate. They exchanged several letters, which, in my opinion, contributed to the development of the MT method. I'm mentioning about this debate because almost 10 years later, another debate was on. And on this debate, the sides were D'Arseville and Kunitz on one side, and Rankin on one side, and on the other side is Weaver. I wanted to mention about this debate because this debate was on the fault studies using EM. D'Arseville and Kunitz paper is probably one of the earliest studies, theoretical studies of faults using EM. They assumed a vertical boundary on both sides of the boundary, they assumed two different conductivity values, and they calculated the response of another layer for different cases. Theoretically, they assumed a fault. Rankin paper, and published in the same issue of Geophysics that year, assumed two vertical boundaries. In other words, he assumed a dike, and he calculated the response. 1 year later, after that, we were opposed their idea, just like Waite opposed Garnier. And they, there's the Bulent nets, and Rankin replied back, and eventually we were said, it seems therefore that some caution must be exercised in trying to apply the theoretical solutions for the fault and dike models to a practical situation. In my opinion, this statement should be still valid. We need to be cautious about it. Before moving on to practical studies, it's also important to mention the paper by Ting and Holm, published in 1980. The Rankin paper was considering the dike to be infinitely long in the third dimension. But this study, Ting and Holm's study, assumed and proved us that the length extension of this dike is important. And variation in that influences the EM responses, especially if you are dealing with two-dimensional modeling. They proved us that the TE mode might create erroneous results. And this started a school of thought, and some group of scientists are cautious, let's say, using the TE mode when they are performing two-dimensional. Practical studies on strike slip faults may also go back to mid-70s. Here, I would like to mention studies by Reddy et al. Based on San Andreas Fault, and Leastways et al. Again, San Andreas Fault. Third paper, it was published by the EM research group of the active fault, targeting the Yamasaki fault. All three of these studies were published in the Journal of Geomagnetism and Geoelectricity. I got this figure, this graph, from the Yamasaki paper, fault paper. I think it tells quite important things. That's why I want to list them to you. Firstly, it's apparent resistivity versus distance plot. In those days, it was common to plot the apparent resistivity values along the profile. And this zero line here is representing the position of the Yamasaki. What we are seeing here is that with one single frequency, by the way, this is plotted for 8 Hertz, and 8 Hertz is very close to the fundamental frequency for Schumann resonances, which is 7.8, I guess. So it tells quite important results, as I said. The first result is it's saying us that the fault zones are conductors. They are telling this is a very important output, and it's an output that we still use today. I mean, we are almost saying the same thing, and we are using like 40 frequencies or 60 frequencies. What I'm trying to tell you is that even one single frequency matters. It's might be very important to pace after the information in our data. Thirdly, it's important because it's kind of a selfish or a naughty habit. It's important because some members of this group came to Turkey and they made an experiment on North Anatolian fault. It's the İsmet Paşa Gerede segment of the North Anatolian fault. We produce a similar figure to Yamasaki fault. What I'm trying to tell you is that the history of EM is quite old in Turkey, and these are the related evidences for that. These days, Kyoto University group is conducting a project on this segment, and they are trying to get results for 3D Globally, tremendous amounts of studies were performed on strike slip faults since the 70s. Here I projected only a few of them. The ones I got from the authors, actually. So there are many studies, and hundreds of them are available right now. So people are eager to study strike slip faults or faults in general by using MT. So I would like to, although our main target is focusing on the Red Sea Transparent Fault, East Anatolian Fault, and the North Anatolian Fault, I would like to elucidate 6 global studies without going into too much detail. My first global example is from Alpine Field in New Zealand. This is in fact a sad slide for me because this study was performed by Dr. Wanamaker and his colleagues, and I received this model 2 weeks before his passing away. So it's kind of a sad, but it is a really marvelous study where they studied the Marlborough strike slip fault system of the northern South Island, where a transpirational regime promotes the evolution of the subduction zone. The authors deployed 67 wideband MT sites on a northwest-southeast aligned profile, and they modeled their data in 2 dimensions. They used TM plus tipper. In other words, they used the Ting and Ullman approach. Here is their output. They plotted their model down to 100 kilometers, and they imaged some conductive zones, some pockets of conductors, I should say, and they interpreted these pockets of conductors as fluids ascending from the nearby subduction. These plus signs over here are earthquakes related to the subduction. And it's quite interestingly, each pocket is somehow corresponding to a fault line above. It's quite a nice piece of work. My second example is from San Andreas Fault in California. You may know that San Andreas Fault is one of the most studied transport faults. This argument is valid for most of the disciplines, and EM is not an exception. If you check the activity, EM activity on San Andreas Fault, you will find Martin Ansford's and his colleagues' studies, Paul Petrosian's studies, or Mihai Beken's studies. There are many valuable examples, but I just wanted to show you the recent one. This is a study performed in the southern San Andreas Fault, and output of it is shown as a profile here. You can easily, I can tell you that there's the C1 anomaly, which can be the fault zone conductor. There are 2 prominent E conductors, C2 and C3, one of which might be serving as contributing to the earthquake activity, because these pink dots over here are showing us the earthquakes that are minor earthquakes probably. Location. This is another remarkable, recent, and interesting study by Usui et al. From Japan. This 2-dimensional study attempts to decipher the conductivity structure near Ototsugawa Fault. There are some other auxiliary faults. Usui-san is actually is a 3D code developer, I should say, but this is also a very nice study by him and his group. They used 2 different sources of information while realizing this study. They used wideband MT sites these blue triangles are showing us the wideband MT sites. And they also used wideband MT plus networking as a database. These pink lines are showing us the long dipoles. In later stages, they projected these dipoles and they applied some kind of an algorithm to calculate the proper electromagnetic impedances. So they modeled wideband MT and they modeled wideband MT plus networking separately. And eventually, I'm just projecting the second one. Their results are quite near to each other, similar to each other. So that's not an issue. They found 3 different conductors in the lower crust, which they pointed out as fluid-rich lower crust, and they these are representing aseismic shear zone and strain accumulation in the region. Asia, and particularly China, accommodates several intercontinental strike slip faults, and they are studied. The names of these faults are Jiaili, Jiangshui, or Red River Fault, Altendale Fault. Since our time is limited and since our focus region is Eastern Mediterranean, I will only mention the largest studied one, which is the sinistral Altendale Fault. It's approximately 2,000 kilometers long, and it is actually the northern boundary for Tibetan Plateau. The recent results, the history of EM studies on Altendale Fault goes back to the year 2000, I guess. I'm showing 2 from one group, studies. One of them is showing us the eastern termination of Altendale Fault, where the one single line, fault line, gets into several branches and having a reverse character. It's like slip faults return, converting into reverse character. What we are seeing here is this profile in the east. And another study is performed on the Aksai region. It's the double restraining band. They claim, the authors are claiming that this band is causing the magnitude of the earthquakes. It changes the magnitude, affects the magnitude of the there. Pahayao fault zone was studied by Bunchai-suk et al. With 3D-dimensional. The authors deployed 31 wideband sites, and they focused onto a region where there are 2 important fault segments, Mai Lao segment and Pan segment. And what they claim is that they found this anomaly called ML, which contributes to the earthquake sequence, corresponds to the earthquake sequence of 2014. And my final global example is from Kamal et al. And they attacked to a debated area in Central Asia or orogenic belt by setting up a north-south aligned profile, which is approximately around 350 kilometers profile long. And they used both magnetotelluric and telluric sites. And they aim to investigate 4 different zones. They are the lake zone, the Altai zone, the Trans-Altai zone, and the South Gobi zone. And these zones are separated by fault lines, so you can see traces of those faults on these. Levant, Fertile Crescent, Mashriq, Middle East, Western Asia, Asia Minor are some of the phrases that define this similar geographical region in the eastern part of the Mediterranean, which is not only politically but also geologically complicated area. This area and the neighboring regions evolved by the amalgamation of bits and pieces of ocean floor, positioned between Laurasia and Gondwana. And the ocean between them, which we call the Neothetis, converged since the early Cretaceous. Convergence of these resulted in the establishment of 5 distinct zones, and their interaction still defines the tectonic regime shaping the region. The push of the Arabian plate here not only promotes the evolution of the Dead Sea transform group, it also causes the Anatolian plate to move westwards along these 2 major fault lines, the East Anatolian fault and the North Anatolian fault. This is one force that is pushing the other force is applied by this subduction zone, which is, let's call it the pulling. Okay? This subduction is quite old. That's why there's slab rollback. So the push and the pull is basically shaping the activity or the activity in this zone. There are many models that attempt to explain the evolution of the region. Let me mention on 3 of them in order to show you the variety of interpretation. First model can be considered as one of the most, let's call it the delamination model, because it involves the subduction of a slab, elimination of that slab. The dismantle wedge over here is filled with asthenospheric flow, and the asthenospheric flow eventually causes an uplift, which is announced to be as high as 2 kilometers, according to some studies. This model also explains the quaternary volcanism, and it also explains the faulting mechanisms here. Another model is called, let's call it the trip tectonics. It's an ingenious model, but let me explain it to you. According to this model, there's a slab detachment. The slab is dripping inside the viscous asthenosphere. So if you drop something heavy inside the viscous material, it will bounce back, rebound. So their idea is claiming that the region was formed or evolved with this mechanism. Third model, let's call it hybrid model or delaminational drip model, assumes that there's a slab detachment. Both asthenospheric and lithospheric material rise up to goes for the uplift and the quaternary volcanism. As you can see, these models, each of them are somehow conflicting with each other, but all of them agree that there is faulting, there is volcanism, and of course there is here I'm showing you a collage of the 3 major complementing transform faults of the Eastern Mediterranean, the Dead Sea transform fault. Here is the Hatay triple junction, and then comes another triple junction. They are overlapping here. This is the East Anatolian fault, and from Orlova triple junction on, we are looking at the North Anatolian. These 2 are sinistral, but the North Anatolian fault is dextral faults. I prepared 3 different examples from each fault line. The EM results I'm talking about. So let me start with the Dead Sea case, Dead Sea transform fault. Dead Sea transform fault is believed to be separated into 2 sections, the northern part and the southern part. And the southern, the division is made by Ben Abraham et al. They claim that the division takes place around 33 degrees 10 minutes. Unfortunately, the studies that I'm going to show you on are present for the southern portion. Arable fault, and the other 2 are from the Dead Sea basin part. The fault here, the structure here is not a complete horse graben system. It's a half graben system. So one side is higher than the other. Okay, I will begin with a study performed on the Arable fault by Röder and Teska. It's a SHOTEM study. In other words, it's short offset transient electromagnetic study targeting to resolve the shallow structure. The authors collected 72 in-loop soundings on 6 profiles with varying lengths and orientations and with 50 meters side separation. Eventually, they modeled their data with 1D occurrence and 1D marquardt inversions. Later on, they projected their results into 2D and 3D by means of forward modeling. Here are the 2D and 3D results, and eventually the authors claimed that the faults act as a boundary in the western and the eastern part. The result reminds me of the earlier study performed in the same fault line by Ritter et al. But of course, their depth extents are quite different. In a way, they are claiming that the fault line is acting like a barrier for the fluid flow. Next, we approximately move to 150 kilometers up to north. This is another systematic study performed on the Dead Sea transform fault with a project name called Desire or Desire. It involves a 2D study and a 3D study. The Dead Sea Basin is one of the world's largest pull-apart basins. It's about 150 kilometers long, and it's one of the probably the most saline basin. It's 10 times the salinity of seawater. The basin evolved between Arable fault and in the south and Jericho fault in the north. It's an echelon system forming a pull-apart basin. It's considered as I said, half graben, and the salinity of it comes from the late Miocene connection to the Mediterranean Sea. Later on, the connection was cut, and Al Lisan Lake formed. Al Lisan Lake is the Dead Sea western terminology, I guess. The profile is targeted at the boundary area and separates the boundary area that separates the northern and southern subbasin of that basin. Authors deployed 150 observations on 2 profiles. The first profile is this one. There is another auxiliary profile. The first profile is made up of 94 measurements, and the second profile is made up of 59 observations. 3 days of recording at each site was performed. 2 teams with 30 instruments. The site separation was varying between 500 meters to 2 kilometers. Following the dimensionality analysis and strike angle determination, the data were inverted by using McKee's code. The mesh included topography, and to deal with the static shifts, the apparent resistivity data were fed with very high error floors. Eventually, the RMS value of 1.8 was achieved. And when we examine the model quickly, we can observe the quaternary aged Al Lisan Samara formations reaching down to 4 kilometers. On both sides of the profile, there are 2 highly resistive basement rocks, obviously, and between them is a highly conductive anomaly which extends to 80 kilometers. It's only 40 kilometers is shown here, but sensitivity tests prove that this anomaly is reaching down to 80. This study was later on extended to include a 3-dimensional interpretation, published almost 3 years later. And the authors modeled their data using ModEM this time, which is based on nonlinear conjugate gradient. And they tested different versions such as they applied nested mesh, or they tried different initial modes or different. With this slide, we move on to East Anatolian Fault. Unfortunately, we are jumping over the study area. I mean the earthquake area. Among all these three fault lines, East Anatolian Fault is the least studied one. As part of the East Anatolian project, the Alberta group and Turkov et al. Targeted to resolve the regional structure as well as the East Anatolian fault system with long period and wideband MT data. I happened to have some chance to join their fieldwork for a couple of days. Firstly, I will show you the results achieved from two long period profiles. The first profile cuts the East Anatolian fault around Elazığ area. This second profile meets the termination of the Karlova triple junction. So this is the triple junction I was mentioning. This profile is that area. Result is here. Turkoğlu et al. Hypothesized that the Eastern Anatolia is a minor version of Tibet, and the Arabian collision to Eastern Anatolia is quite similar to Indian plate colliding with Asia. According to their interpretation, the major difference between these zones is that the conductors found in East Anatolia at crustal depths appear as smaller pockets rather than widely distributed ones observed in Tibet. So this is from a review paper by Martin Answer and showing us the situation in Tibet. Following the long period results, Turkoğlu focused on the East Anatolian fault by using wideband data and long period altogether. They used 20 observations. 10 of them belong to wideband and 10 of them long periods measurements. They made a dimensionality analysis and strike angle determination. And they found a value of something like 75 east, which was utilized for the rotation, of course. They modeled their data jointly. I mean, they used DE and EMs all together and deeper data. The error floors were taken as 20% for intensity and 5% for base and 0.02% for dipper. Even obviously they gave weight to the phase for these reasons. And eventually they managed to reach to an RMS value of 1.4 for this profile. They attacked the static shift problem during one. The authors claim mid-crustal conductor C2 around 10 kilometers beneath the East Anatolian fault surface trace, where the brittle ductile transition is known to be around 20 kilometers. Second prominent conductor is denoted as C4 here, and they are coinciding to the sedimentary deposits of the Arabian platform. Same study by Turkoğlu et al. Shares a second profile, but this time on the North Anatolian fault. So this profile, we entered the North Anatolian fault region. Important because this article is providing a nice comparison between the East Anatolian fault and the North Anatolian. North Anatolian fault profile is made up of 9 long period observations and 4 wideband stations. The strike analysis pointed out an angle of north 105 east, and they used similar parameters I mentioned in the earlier slide for 2-dimensional modeling and reached to a MS value of 1.4. Most prominent result on this profile is probably this C5 anomaly that we can call as a Boltzmann conductor. Although the resolution of the station is not so high, and gives us a hint about the structure here. They also point out that there are some discrepancies between the conductors of East Anatolian fault and San Andreas fault. And the probable reason for these differences originates from the maturity of the. Okay, I'm stepping quite a long distance from somewhere here to here, and I want to move on to an overview study by Honker et al. This paper is not a classical MT paper. In fact, it's as a quite a long story, but I will tell you very shortly. Turkish-Japanese MT project started its MT observations in June 1999 with the southern branch of the Bulent fault. Actually, 16th of August 1999, 4 of these wideband MT stations were recording the northern Bulent fault. A couple of hours later, 7.4 seismic earthquake took place. Here we can compare the 5-channel recordings of the MT data and together with the recordings of the nearby seismometer during the earthquake. The seismometer is somewhere around here. Obviously, the MT instruments acted like a seismometer and recorded the earthquake. Almost 1 month later, a second survey was designed and measurements were repeated at some of the sites. The result of this, the study, the authors attempted to prove that the resistivity values observed right before the earthquake returned to their original values for the earthquake. It took almost 1 month. I think this was a important remarkable outcome regarding the time dependency of resistivity variations at fault zone. The authors interpret such changes as pressure-induced transition between isolated and interconnected fields. The next piece of work is an offshore study performed in the Marmara Sea here. Where the North Anatolian fault divides into 2 branches near Çınarcık area, Çınarcık Basin. For this purpose, Jamstack, Tokyo Institute of Technology and Observatory was university scientists. We realized ocean bottom MT project. And the support was provided by the Turkish Navy at the time. We deployed 14 different OBMs at the ocean floor, sea bottom. Later on, Kaya et al. Adapted the 2D code of Ogawa and Uchida for ocean use and analyzed a combination of the OBM data together with the land data. This profile is analyzing the both data, ocean bottom data and land data. Somehow the results confirmed the earlier models, such as this one. And the westward progression of the probable conductor to the west. Later stages, the group deployed more OBM studies further to the west of Marmara, somewhere here. So I don't have any information about that area. With this slide, I'm wrapping up the examples that I'd like to present you. There are some more studies on the North Anatolian fault, mostly developed by my former students. The first one is by Sinan Özaydın, central enough, central North Anatolian fault near Tosya. Another one is focusing to the Arable Peninsula. Third one is on the other side of Marmara, somewhere here, the Danos fault. These all of were 3-dimensional study. Okay. This was a narrative review. That's why I am not going to go into the discussions too much. But before concluding, let me show you the situation. We have 2D versus 3D results performed on these faults that I've been mentioning. So this is, for example, the 2D result for the sea transform fault. This is the 3D one. East Anatolian fault, there is no published 3D results. So when it comes to the ocean floor study, there is a initial result for 3D and 2D result is shown here. On land, in the area, we have a 2D result and a 3D result. Of course, they are not identical. Nobody is expecting them to be identical, but we have many things to work on. Still, we need to make a lot of progress for that. Second conclusion slide is following the shallow structure and the fault zone conductors comparison. We know that there is no fault zone conductor defined for the Dead Sea transform fault, in particular for the Arable fault area. For North Anatolian fault, we know that there is it's like 700 meters and locked one near Panos. And for San Andreas, we have a 3 kilometer locked. And for a creeping region, we have a 6 kilometer depth fault zone. So that brings the question why there is a difference between these faults when it comes to fault zone conductors. That's another question that comes to all. And my final conclusion figure is providing a comparison between the deep structure. This is a general classification provided by Ritter et al. And they classified the upper crust and lower crust in 7 different versions. And here are some of the that we can compare. This is from this is Alpine Field. This is for structure. This is let's see transfer flow. I am concluding my speech. Fluids may have an essential role in the earthquake generation, and looking or investigating the fluids in a depths, we might be able to decipher the structure. So it's an important relationship to be focused on. And the fluid presence, of course, can be detected by the EM methods almost all. It was a narrative review based on the electrical structure of the transform faults. I tried to give a historical and global perspective to this topic. And I focused on the 3 major strike slip faults, transform faults of the Eastern Mediterranean. One final slide is I would like to, this is an unofficial invitation. If any of you are interested in working in the new earthquake area, it's a very broad area. It's around 300 kilometers long. It gives an example for stress transfer. And learn more about the faults and fluids interaction, so relationship. And we definitely need to learn more about the tectonics of the triple junctions, and by means of MT, by using MT, we can learn more about it. That's why I wanted to invite make an international call and invite scientists or groups to study this area. Thank you. This ends my talk.
Well, thank you very much, Bulent. That was an absolutely wonderful and very timely presentation of strike slip faults, given what's happening in your country. Just a general question, I guess, from me before we go to the other questions and they're beginning to roll in. Please send your questions in the Q&A. So the interpretation of these conductors lying within the fault zone is of fluids.
Mm-hmm.
Saline fluids.
Yes. You're asking whether these are saline fluids.
Yeah, I'm just wondering about these bright conductors we see in many of the models of fault zones.
Let me open You mean, yeah, these ones?
Yes, yes. In most of the models you've
Yeah,
shown.
I don't
except-
think it depends on which depth you are focusing, or which areas you are targeting, because it can be partial melts as you go deeper. For example, when we talk about the Alpine Fault example, you know, this is a subduction zone, and serpentinization is causing some dehydration. So it might be related to dehydrated minerals, fluids there. But when it comes to a shallow structure, it might be saline fluids. Yes, might be related to. So it depends on the. That's why I wanted to mention that with MT we can cover a broad depth range by using different frequency. Hence, you can focus on the different problems related to faults, the origins of the fluids. It might be different.
Have you seen any correlation of the strength of the conductor with the strength of the earthquakes? My thinking is that the more fluid you have, the more lubricated the fault zone will be. So perhaps the more minor the earthquakes might be when it slips.
Yeah, we know that fluids are influencing the earthquake generation, but it's very difficult to answer your question. I really don't have a proper answer for that. So if the fluids are more, what happens? Really, I don't know. It depends.
Yeah.
I mean, each fault line might be acting according to its structure or its maturity. There are many factors that are influencing the faults and fluids.
Yeah. Well, this idea leads right into the very first question, which is from Richard Smith, who says that you say the study before and after the earthquake was interpreted to be due to stress changes. Could it also be changes in fluid? Is there a corresponding change in resistivity below the base of the brittle zone?
Sorry, I couldn't hear the question. Can you repeat it again?
Okay, if you click on Q&A, you'll see the question. I'm just repeating it for the recording.
Yes. Of course, the character of the fluid might be influencing the character. Corresponding change in the resistivity below the base of the. It depends on again from fault to fault. It has changed. It must be changing. I really don't have an answer for that, because each fault has and as you know, in T we are poor in detecting deep conductors, so it's difficult to be strictly tell that this the conductivity value of the that depth is certain. So there must be some kind of relationship, of course, but it's quite difficult to detect.
Yeah. Are there any other questions from the audience? We have a question from Abbas Fanay. Thank you for your informative presentation. Do you study the dam effects, such as Eliso and Ataturk, or new dam over the last decade in Turkey, on correlation to earthquake generation?
No, I have never studied on that, but it might be interesting to have a controlled experiment, of course. It might be interesting to conduct such a thing.
Yeah, that's a very interesting question, Abbas. So we don't have any more questions. Perhaps just one more from me. Do you have any information of the geochemistry of the fluids that are coming up through the fault zone? Do you know whether from the deuterium ratios, whether they're meteoric or metamorphic fluids, and from
I don't have
carbon
much information about.
Okay, yeah.
I don't have much information about the geochemistry of the fluids.
Okay, yeah. Be interesting to see whether they're mantle-derived fluids or
That's
meteoric fluids going down and coming back up. Okay, well, thank you very much again, Bulent. Absolutely wonderful presentation, and I'm sure everyone in the audience got a huge amount out of this. So thank you very much again, and I welcome everybody to join us in a month's time. And I see some of these people are sending thumbs up and and some reactions. Absolutely brilliant. Thank you, everybody. See everyone in a week's time. Bye for now. And the recording will be available in a couple of hours, and the presentation when Bulent sends it. Bye, everybody.